Cavitation damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of cavitation damage mechanisms based on API 571. The first is cavitation is a form of erosion caused by the formation and instantaneous collapse of innumerable tiny vapor bubbles. The second is the collapsing bubbles exert severe localized impact forces that can result in metal loss referred to as cavitation damage. And the third is the bubbles may contain the vapor phase of the liquid, air or other gas entrained in the liquid medium. Cavitation damage is a form of material degradation caused by the formation and subsequent collapse of vapor bubbles in a liquid. This phenomenon occurs when the pressure in a liquid drops below its vapor pressure, leading to the creation of these bubbles, which are primarily filled with the liquid's vapor. The bubbles, also known as cavities or voids, grow and expand in regions of low pressure. When these bubbles are transported to regions of higher pressure, they violently collapse. Here's a breakdown of the process and its effects. Number 1 is cavitation process, include. The first is bubble formation, or cavitation. A liquid experiences a localized pressure drop, for example, due to the high-speed flow around a propeller blade, the vibration of an ultrasonic transducer, or the rapid pressure changes in a pump. If the local pressure falls below the liquid's vapor pressure, the liquid vaporizes, forming bubbles. The second is bubble growth. The bubbles grow as more liquid vaporizes into them, and they may also coalesce with other bubbles. The third is bubble collapse. As the bubbles move into regions of higher pressure, they become unstable and violently collapse. This collapse is extremely rapid and generates several key effects. The fourth is impact and damage, include. Microjets. The asymmetric collapse of a bubble can create extremely high-speed jets of liquid, which are directed towards the nearby solid surface. These jets can impact the surface with pressures exceeding 1000 MPa, 10,000 atmospheres. Shock waves. The bubble collapse also generates powerful shock waves that radiate outward through the liquid. High temperatures. Localized temperatures at the point of collapse can reach thousands of degrees Celsius, though these are extremely short-lived. Number 2 is cavitation damage mechanisms, include. The intense impact forces, shock waves, and high temperatures generated by the bubble collapse lead to various forms of damage. The first is erosion. Repeated impacts from microjets and shock waves gradually erode the material surface, leading to pitting, gouging, and material removal. This is the primary cause of cavitation damage. The second is fatigue. The repeated stress cycles imposed on the material by the collapsing bubbles can lead to fatigue cracking and eventual failure. The third is material degradation. The high temperatures can lead to localized melting, thermal stress, and changes in the material's microstructure, further weakening it. The fourth is corrosion acceleration. Cavitation can remove protective surface layers, such as oxides, exposing the underlying material to corrosive environments and accelerating corrosion. Number 3 is factors influencing cavitation damage. The severity of cavitation damage depends on several factors. The first is liquid properties. The liquid's vapor pressure, viscosity, and surface tension influence the ease of bubble formation and collapse. The second is pressure fluctuations. The magnitude, frequency, and duration of pressure drops significantly affect the intensity of cavitation. The third is material properties. The material's hardness, ductility, fatigue strength, and corrosion resistance determine its susceptibility to cavitation damage. Harder materials generally resist cavitation erosion better than softer materials. The fourth is flow conditions. Flow velocity, turbulence, and geometry of the flow path affect the intensity and location of cavitation. Number 4 is examples of cavitation damage. Cavitation damage is a significant problem in various engineering applications. The first is hydraulic machinery. Pumps, turbines, propellers, and valves can experience cavitation damage, leading to reduced efficiency, noise, vibration, and ultimately, equipment failure. The second is engines. diesel engine cylinder liners can suffer cavitation erosion due to the collapse of bubbles near the liner surface. The third is ultrasonic cleaning. The cavitation created in ultrasonic cleaning baths is used to remove dirt and contaminants. However, it can also cause damage to delicate parts. The fourth is medical applications. Ultrasonic devices used in medical imaging and therapy can, in some cases, lead to cavitation, which can affect the surrounding tissue. The fifth is aerospace. Cavitation can occur in fuel pumps and other components of aircraft, posing a threat to flight safety. Cavitation damage is a complex phenomenon involving bubble formation and collapse in liquids, resulting in severe material degradation due to the intense pressures, temperatures, and shock waves generated. It is a significant concern in many engineering applications, and careful design, material selection, and operating practices are necessary to mitigate its harmful effects. Cavitation damage mechanisms affected materials based on API 571. Most common materials of construction including copper and brass, cast iron, carbon steel, low alloy steels, 300 series SS, 400 series SS and nickel base alloys. Cavitation damage can occur on various materials, including but not limited to. Number 1 is alloys. Cavitation damage can occur on alloys such as steel, stainless steel, titanium, and aluminum, especially under high cyclic stresses and pressure fluctuations. Number 2 is cast iron. Cast iron is prone to cavitation damage due to its low tensile strength and high compressive strength, making it susceptible to erosion-corrosion in fluid flow systems. Number 3 is copper and copper alloys. Cavitation damage can occur on copper and its alloys, particularly in marine applications due to seawater corrosion. Number 4 is titanium alloys. Titanium alloys, used in marine and aerospace applications, are susceptible to cavitation damage due to their high strength-to-weight ratio and low ductility. Number 5 is nickel-based alloys. Nickel-based alloys, such as Inconel and Monel, are resistant to corrosion but can still experience cavitation damage due to high fluid velocities and pressure fluctuations. Number 6 is piping materials. Various piping materials, including carbon steel, stainless steel, and ductile iron, can be affected by cavitation damage due to fluid flow, pressure surges, and corrosion. Number 7 is welds. Welds in metals can be more susceptible to cavitation damage than the base metal, especially if the welding process or joint design exacerbates stress concentrations. Number 8 is concrete. Cavitation damage can occur on concrete surfaces, particularly in areas with high fluid velocities or pressure fluctuations, such as dam intakes or pump stations. Number 9 is plastics. Some plastics, like polyurethane, polyvinyl chloride, PVC, and acrylics, can be affected by cavitation damage due to the formation of microbubbles and erosion. Cavitation damage can occur in various environments, including: Number 1 is freshwater systems. Number 2 is seawater systems. Number 3 is industrial processes, such as chemical processing, oil refining. Number 4 is power generation systems, such as hydroelectric power plants. Number 5 is transportation systems, such as pumps, valves. Number 6 is marine vessels and equipment. When cavitation damage occurs, it can lead to significant material degradation, loss of performance, and even catastrophic failure. Regular inspection and maintenance can help prevent cavitation damage and extend the lifespan of affected equipment and structures. Cavitation damage mechanisms. Critical factors based on API 571. The first is in a pump, the difference between the actual pressure or head of the liquid available, measured on the suction side, and the vapor pressure of that liquid is called the net positive suction head, NPSH, available. The minimum head required to prevent cavitation with a given liquid at a given flow rate is called the net positive suction head required. Inadequate NPSH can result in cavitation. The second is temperatures approaching the boiling point of the liquid are more likely to result in bubble formation than lower temperature operation. The third is the presence of solid or abrasive particles is not required for cavitation damage but will accelerate the damage. Cavitation damage is a complex phenomenon, and the critical factors influencing it can be categorized as follows. Number 1 is fluid properties, include. The first is vapor pressure. A lower vapor pressure makes it easier for cavities to form. Fluids with lower vapor pressures are more susceptible to cavitation at a given pressure. The second is surface tension. Higher surface tension resists cavity formation and collapse, reducing cavitation intensity. The third is viscosity. Higher viscosity can dampen the collapse of cavitation bubbles, potentially reducing impact forces. However, high viscosity can also hinder the flow and contribute to pressure drops. The fourth is gas content. The presence of dissolved gas can affect the collapse behavior. More gas can cushion the collapse, but it can also influence the number and size of cavitation bubbles. The fifth is temperature. Temperature influences vapor pressure and other fluid properties, indirectly affecting cavitation. Higher temperatures generally increase vapor pressure, making cavitation more likely. Number 2 is pressure conditions, include. The first is pressure fluctuations. The magnitude and rate of pressure changes are critical. Rapid and significant pressure drops below the vapor pressure are necessary for cavitation inception. The second is minimum pressure. The lower the minimum pressure reached, the more intense the cavitation and potential for damage. The third is pressure distribution. The spatial distribution of pressure gradients can determine where cavitation occurs. High-pressure gradients are favorable for cavitation. Number 3 is flow characteristics, include. The first is flow velocity. Higher flow velocities increase the kinetic energy available for pressure drops and cavitation bubble collapse. The second is flow geometry. Sharp edges, changes in cross-section, and other geometric features can create regions of low pressure and promote cavitation. Examples include. Flow geometries. Example 1 is valves and orifices. These are common sites for cavitation due to high flow velocities and pressure drops. Flow geometries. Example 2 is impellers and pumps. Rotating components with changing blade geometries are prone to cavitation. Flow geometries. Example 3 is nozzles and diffusers. Areas of flow acceleration and deceleration can create cavitation conditions. Flow geometries. Example 4 is hydrofoils. The low-pressure region on the suction side can lead to cavitation. The third part of flow characteristics is flow turbulence. Turbulent flow can enhance the mixing and transport of cavitation bubbles, potentially spreading the damage. The fourth part of flow characteristics is frequency of pressure fluctuations. The frequency of pressure pulsations or oscillations can influence the rate of bubble generation and collapse, affecting damage rates. Critical factors. Number 4 is material properties. The first is material strength, tensile strength. Hardness. Materials with lower tensile strength and hardness are more susceptible to damage from the impact of collapsing bubbles. The second is fatigue strength. Repeated cavitation impacts can lead to fatigue failure, even if the initial impact doesn't cause immediate damage. The third is elasticity. The elastic properties of the material affect its ability to absorb the energy of bubble collapse. More elastic materials might better withstand the impacts. The fourth is corrosion resistance. Cavitation damage often removes protective surface layers, such as oxide films, which can accelerate corrosion. The combination of mechanical erosion and corrosion can be highly detrimental. The fifth is acoustic properties. The material's acoustic impedance can influence the propagation and reflection of pressure waves generated during bubble collapse, potentially affecting damage patterns. Number 5 of critical factors is cavitation bubble dynamics. The first is bubble size and distribution. The size of the bubbles and the distribution of bubble sizes influence the energy released during collapse. The second is bubble collapse location. The proximity of bubble collapse to the material surface is critical. The third is shock waves. The intensity and frequency of shock waves generated by the bubble collapse. The fourth is microjets. the formation of high-speed microjets during asymmetric bubble collapse can cause significant localized damage. Number 6 is operating conditions, include. The first is system pressure. Overall system pressure affects the likelihood of cavitation. Higher system pressure can shift the range of flow conditions where cavitation occurs. The second is flow rate, affects the velocity and pressure gradients. The third is fluid quality. The presence of contaminants or particles in the fluid can influence the cavitation process. The fourth is operating time, the duration of exposure to cavitation conditions. Cavitation damage results from the complex interplay of these factors. The critical factors that dominate in a specific situation depend on the application. Understanding the influence of these factors allows engineers to design systems to minimize or eliminate cavitation, or to select materials that are more resistant to the damaging effects. Methods to mitigate cavitation include modifying flow geometries, increasing system pressure, selecting appropriate fluids, and using cavitation-resistant materials. Cavitation damage mechanisms affected units or equipment based on API 571. The first is cavitation is most often observed in pump casings, pump impellers, low pressure side, and in piping downstream of orifices or control valves. The second is damage can also be found in restricted flow passages or other areas where turbulent flow is subjected to rapid pressure changes within a localized region. Examples of affected equipment include heat exchanger tubes, venturis, seals and impellers. Cavitation damage affects a wide range of units and equipment where liquids experience rapid pressure changes. Here's a breakdown of common affected units or equipment. Number 1 is pumps, include. The first is centrifugal pumps. These are particularly vulnerable due to the pressure drop at the impeller inlet. The impeller blades, casing, and volute are susceptible. The second is reciprocating pumps. Cavitation can occur at the inlet valves and cylinder walls. The third is other pump types. Any pump type is potentially at risk, especially in high-speed or high-pressure applications. Number 2 is hydraulic systems, include. The first is hydraulic cylinders. The cylinder barrels and piston rods can suffer damage. The second is control valves. Valves, especially those controlling flow or pressure, are prone to cavitation in the valve seats and bodies. The third is hydraulic pumps and motors. Components are affected similarly to standalone pumps. The fourth is piping and fittings. Pressure drops at bends, restrictions, or changes in pipe diameter can initiate cavitation in the pipes themselves. Number 3 is turbines, include. The first is hydro-turbines, such as Francis, Kaplan. The runner blades are highly susceptible to cavitation. This is a major concern in hydroelectric power generation. The second is steam turbines. Cavitation can occur in the low-pressure stages where the steam condenses. Number 4 is propellers and marine equipment, include. The first is ship propellers, a very common site for cavitation. The blades, especially the leading edges, are highly vulnerable. The second is underwater vehicles, such as submarines, torpedoes. Propellers, rudders, and control surfaces are all at risk. The third is water jets, similar concerns to propellers. The fourth is marine engines. Cavitation can affect cooling systems and other components. Number 5 is diesel engines, include. The first of diesel engines is fuel injectors. The small orifices in fuel injectors are susceptible to cavitation, affecting fuel atomization and engine performance. The second of diesel engines is cooling systems. Cavitation can occur in the water jackets around the cylinders and in the water pump. The third of diesel engines is cylinder liners. If cavitation occurs in the cooling system, it can lead to pitting and erosion of the cylinder liners. Number 6 is valves and orifices, includes. The first of valves and orifices is control valves. In general, any valve regulating fluid flow is at risk, particularly if there's a significant pressure drop. The second of valves and orifices is orifices and flow meters. Cavitation can occur at the vena contracta, narrowest point, in orifices used for flow measurement. Number 7 is medical devices, include. The first of medical devices is ultrasound transducers. High-intensity focused ultrasound systems can generate cavitation bubbles for therapeutic purposes, but this needs to be carefully controlled to avoid unintended damage. The second of medical devices is medical pumps. Pumps used in medical devices like dialysis machines or infusion pumps can be affected. Number 8 is mixing and agitation equipment, include. The first of mixing and agitation equipment is impellers and stirrers. In mixing tanks and reactors, high-speed impellers can create cavitation in the liquid. The second of mixing and agitation equipment is sonochemical reactors. These reactors deliberately use cavitation to enhance chemical reactions, but the equipment must be designed to withstand the effects. Number 9 is aerospace applications, include. The first of aerospace applications is rocket engines. Cavitation can occur in the fuel and oxidizer pumps. The second of aerospace applications is high-speed aircraft components. Any component exposed to high-speed fluid flow could be at risk, although this is less common than in other applications. In summary, cavitation is a widespread phenomenon. The equipment or units that are most at risk are those that involve. Number 1 is high fluid velocities. Number 2 is rapid pressure fluctuations. Number 3 is presence of liquids that can vaporize under low pressure. Number 4 is sharp changes in geometry which cause changes in pressure. Appearance or morphology of cavitation damage mechanisms based on API 571. Cavitation damage generally looks like sharp-edged pitting but may also have a gouged appearance in rotational components. However, damage occurs only in localized low-pressure zones, see Figure 4:46 to Figure 4:49. Figure 4:46, cutaway of a CS butterfly valve with cavitation damage after 2 years of service due to a high-pressure drop across the valve in a hydrocarbon drain line off a cold low-pressure separator in an atmospheric resid desulfurizing unit. Figure 4:47, closer view of damaged surface of butterfly valve. Figure 4:48, cavitation pitting on the low-pressure side of a stainless steel pump impeller. Figure 4:49, cavitation pitting on the water side of a cast iron cylinder liner in a large engine. Cavitation damage, which is caused by the formation and collapse of cavities or bubbles in a fluid, can appear in various forms depending on the material being damaged and the conditions under which the cavitation occurs. Here are some common morphologies or appearances of cavitation damage. Number 1 is cavitation pits or craters. These are the most common type of cavitation damage. They appear as small, rounded or hemispherical pits or craters on the surface of the material. The pits can be uniform in size and distribution or irregular and randomly spaced. Number 2 is micro or nanoscale cracks. Cavitation can cause the formation of micro or nanoscale cracks, which can propagate to form larger cracks or even fracture the material. Number 3 is surface roughening. Cavitation can cause surface roughening, especially in metals, due to the formation of microcracks or cavities. Number 4 is cavitation holes. Large cavitation holes can form in materials, especially in situations where the cavitation is severe or prolonged. Number 5 is material loss. Severe cavitation can cause significant material loss, especially in situations where the fluid is highly corrosive or the material is weak. Number 6 is pitting or corrosion. Cavitation can accelerate corrosion in materials, leading to the formation of pits or localized corrosion zones. In metals, cavitation damage can be identified by the following characteristics. Number 1 is small, rounded or hemispherical pits or craters. Number 2 is micro or nanoscale cracks or fissures. Number 3 is surface roughening or pitting. Number 4 is loss of surface finish or appearance. Number 5 is material loss or thinning. In composites, cavitation damage can be identified by the following characteristics. Number 1 is blisters or bubbles on the surface. Number 2 is delamination or debonding between layers. Number 3 is cracking or fracture of fibers or matrix. Number 4 is surface roughening or pitting. Number 5 is material loss or thinning. In ceramics or glasses, cavitation damage can be identified by the following characteristics. Number 1 is crazing or cracking. Number 2 is surface pitting or roughening. Number 3 is material loss or thinning. Number 4 is changes in transparency or translucency. It's essential to note that the appearance or morphology of cavitation damage can vary depending on the material being damaged, the operating conditions, and the duration of the cavitation event. Cavitation damage mechanisms prevention and mitigation based on API 571. The first is resistance to cavitation damage in a specific environment may not be significantly improved by a material change. A mechanical modification, design or operating change is usually required. The second is cavitation is best prevented by avoiding conditions that allow the absolute pressure to fall below the vapor pressure of the liquid or by changing the material properties. Examples include: streamline the flow path to reduce turbulence, decrease fluid velocities, remove entrained air, increase the suction pressure of pumps, alter the fluid properties, perhaps by adding additives. Use hard surfacing or hard facing. Use of harder and or more corrosion-resistant alloys. The third captured of cavitation damage mechanisms based on API 571 is attack is accelerated by the mechanical disruption of protective films at the liquid-solid interface, such as a protective corrosion scale or passive films. Therefore, changing to a more corrosion-resistant and or higher hardness material may not improve cavitation resistance. Excessively hard materials may not be suitable if they lack the toughness required to withstand the high local pressures and impact, shear loads, of the collapsing bubbles. Cavitation damage can be prevented or mitigated through various strategies focusing on eliminating or reducing the conditions that lead to bubble formation and collapse. Here's a breakdown of common prevention and mitigation methods. Number 1 is design and operation optimization, include. The first of design and operation optimization is reduce flow velocity, include. Lowering fluid velocity is a fundamental approach. This can be achieved by using larger pipe diameters, optimizing pump speeds, carefully designing bends, valves, and other flow restrictions to minimize localized high-velocity areas. This directly reduces the pressure drop and shear forces that trigger cavitation. The second of design and operation optimization is increase system pressure, include. Increasing the static pressure in the system or at critical locations can prevent the fluid pressure from dropping below the vapor pressure. This might involve the following. Raising the elevation of the fluid source, such as a reservoir. Using pressurized tanks or closed systems. Ensuring sufficient net positive suction head, or NPSH, available for pumps. The third of design and operation optimization is improve hydraulic design, include. Carefully design hydraulic components to avoid sharp changes in flow direction, sudden expansions or contractions, and other features that create pressure drops and turbulence. This includes streamlining inlets, outlets, and passages. Using diffusers to recover pressure. Optimizing the shape and placement of pump impellers. The fourth of design and operation optimization is operate within recommended limits, include. Always adhere to the manufacturer's operating guidelines for pumps, valves, and other equipment. This includes staying within specified flow rates, pressures, and temperatures. Avoid operating pumps at excessively low or high flow rates, often away from the best efficiency point, BEP, as this can increase cavitation risk. The fifth of design and operation optimization is proper valve selection and placement, include. Choose valves suitable for the application's pressure and flow characteristics. Place valves correctly to minimize pressure drops and turbulence. For example, in pump suction lines, gate valves are preferred over globe valves, as they provide less restriction. Number 2 of the common prevention and mitigation methods is material selection in surface treatments, includes. The first of material selection and surface treatments is use cavitation-resistant materials, includes. Select materials that are less susceptible to damage from cavitation erosion. Common choices include stainless steels, such as 316 stainless steel. High-strength alloys, such as nickel aluminum bronze, Ni resist. Cobalt-based alloys, such as stellite. The second of material selection and surface treatments is surface hardening, includes. Apply surface treatments to increase the material's resistance to erosion. These methods include hard facing, applying a layer of a hard, wear-resistant material, e.g., stellite, to the surface. Thermal spraying, applying a coating of a protective material, such as ceramic or metal alloys. Case hardening, surface hardening techniques like carboizing or nitriding can increase surface hardness. Shot peening, introducing compressive stresses on the surface. The third of material selection and surface treatments is protective coatings, includes. Apply cavitation-resistant coatings to vulnerable surfaces. Examples include polyurethane coatings, epoxy coatings, elastomeric coatings, specialized ceramic or metallic coatings. The number 3 of common prevention and mitigation methods is operational practices and monitoring, includes. The first of operational practices and monitoring is regular inspection and maintenance, includes. Implement a regular inspection schedule to identify and address early signs of cavitation damage, such as pitting, erosion, or noise. Regularly inspect and maintain pumps, valves, and other components to ensure they operate correctly and prevent the conditions that promote cavitation. The second of operational practices and monitoring is filtration. Maintain clean fluid, removing any particulate matter or debris in the fluid system. This will reduce turbulence and may help avoid the formation of cavitation bubbles. The third of operational practices and monitoring is air injection. In some cases, injecting small amounts of air or another inert gas into the fluid can help cushion the bubble collapse and reduce the intensity of the impact. This is not a universally applicable solution and needs to be carefully controlled. The fourth of operational practices and monitoring is vibration analysis and noise monitoring, includes. Use vibration sensors and acoustic monitoring equipment to detect the presence of cavitation. Cavitation often produces distinctive noise and vibration patterns. This allows for early detection and intervention. The number 4 of common prevention and mitigation methods is pump-specific considerations, since pumps are common cavitation sites, includes. The first of pump-specific considerations is ensure sufficient NPSH, net positive suction head, include. NPSH available, NPSH, must always be greater than NPSH required, NPSHR, for a pump to avoid cavitation on the suction side. NPSH is a measure of the pressure at the pump inlet, accounting for static pressure, elevation, and frictional losses. NPSHR is a characteristic of the pump itself, specified by the manufacturer, representing the minimum pressure needed at the inlet to prevent cavitation. Carefully calculate NPSH and compare it to the pump's NPSHR across the operating range. The second of pump-specific considerations is proper pump priming, include. Make sure the pump is fully primed before starting it. This involves ensuring the pump and suction lines are filled with fluid and that there is no trapped air. Air in the suction can readily trigger cavitation. The third of pump-specific considerations is control pump speed, variable speed drives, VSDs. Use variable speed drives to control pump speed, allowing for adjustments to maintain optimal performance and reduce cavitation risk based on changing operating conditions. The fourth of pump-specific considerations is optimize impeller design and clearance. In pump design, engineers can use design modifications such as modified impeller blade shapes and optimized clearances to reduce the potential for cavitation. The number 5 of common prevention and mitigation methods is advanced technologies, includes. The first of advanced technologies is ultrasonic techniques. Some research explores the use of ultrasonic vibrations to help break up or disperse cavitation bubbles. This is still largely experimental. The second of advanced technologies is computational fluid dynamics, or CFD. Use CFD simulations to model fluid flow and predict areas prone to cavitation. This helps in optimizing designs and identifying potential problems before construction or operation. In summary, preventing and mitigating cavitation damage is often a multifaceted approach. The best strategy depends on the specific application, the fluid properties, the operating conditions, and the equipment involved. It's usually more effective to prevent cavitation through careful design and operation rather than trying to repair damage after it occurs. A combination of these strategies will provide the best protection against cavitation damage. Inspection and monitoring methods to detect cavitation damage mechanisms based on API 571. The first is cavitating pumps may sound like pebbles are being thrashed around inside. The second is techniques include limited monitoring of fluid properties as well as acoustic monitoring of turbulent areas to detect characteristic sound frequencies. The third is visual examination of suspected areas, as well as external UT and RT can be used to monitor for loss in thickness. Cavitation damage can be detected using a variety of inspection and monitoring methods, which can be broadly categorized as visual inspection, acoustic monitoring, vibration analysis, and performance monitoring. Here's a breakdown of each inspection and monitoring category. Number 1 is visual inspection. The purpose of visual inspection is, this is the most straightforward and often the first step in assessing cavitation damage. It involves looking for physical signs of damage on the surfaces of components. The methods of visual inspection include. The first method of visual inspection is direct visual inspection, requires shutting down the equipment and physically inspecting the components. This can be done using the naked eye, magnifying glasses, or borescopes for inspecting hard-to-reach areas. The second method of visual inspection is to find signs of damage. It is look for pitting that commonly signs such as small, localized holes or craters. Erosion that commonly signs such as material removal, creating rough, uneven surfaces. Cracking that commonly signs such as fine or gross cracks, especially near areas of high stress. Surface changes that commonly sign such as discoloration, changes in surface texture. Number 2 is acoustic monitoring. The purpose of acoustic monitoring is, cavitation generates characteristic noise due to the implosion of vapor bubbles. Acoustic monitoring detects and analyzes these sounds. The methods of acoustic monitoring include. The first method of acoustic monitoring is hydrophones or accelerometers. These sensors are placed in the fluid or on the equipment to pick up the acoustic signals. The second method of acoustic monitoring is ultrasonic testing, uses high-frequency sound waves to detect cavitation activity. The third method of acoustic monitoring is acoustic emission monitoring. This technique uses sensors to detect the stress waves created by the collapse of cavitation bubbles. Acoustic emission is particularly useful for detecting the onset of cavitation. The fourth method of acoustic monitoring is signal processing and analysis. The acoustic signals are processed to identify the frequency components and amplitude characteristics associated with cavitation. The fifth method of acoustic monitoring is data interpretation. Increases in noise levels or changes in the acoustic signature can indicate the presence and severity of cavitation. The sixth method of acoustic monitoring is advantages inspection or detection method, can often be performed online, during operation, provides early detection of cavitation, and is non-intrusive. Number 3 is vibration analysis. The purpose of vibration analysis is, cavitation can induce vibrations in the equipment as the bubbles collapse and generate shock waves. Analyzing these vibrations helps to assess the extent of cavitation. The methods of vibration analysis include. The first method of vibration analysis to be considered is vibration sensors, accelerometers, velocity transducers, or displacement sensors are mounted on the equipment. The second method of vibration analysis is frequency analysis. The vibration signals are analyzed in the frequency domain using techniques like fast Fourier transform, or FFT. The third method of vibration analysis is signature analysis. Look for characteristic vibration frequencies related to cavitation. Often, vibration energy increases at specific frequencies related to the bubble collapse process and its harmonics. The fourth method of vibration analysis is time domain analysis, can be useful for detecting impulsive events. The fifth method of vibration analysis is data interpretation. Increased vibration levels, especially at specific frequencies, often correlated with the cavitation frequency, can indicate cavitation damage. The sixth method of vibration analysis is advantages, relatively easy to implement, can provide online monitoring, and can detect cavitation even if it's not directly producing loud noises. Number 4 is performance monitoring. The purpose of performance monitoring is cavitation affects the performance of pumps, turbines, and other equipment. Changes in performance parameters can indicate the presence of cavitation. The methods of performance monitoring include. The first method of performance monitoring is flow rate measurement. Decreases in flow rate at a constant pump speed can suggest cavitation. The second method of performance monitoring is pressure measurement. Monitoring the inlet and outlet pressures of pumps or turbines. Cavitation can lead to a drop in pressure. Number 5 is continuous improvement. Use data from monitoring and inspections to identify areas for improvement. The fourth method of performance monitoring is power consumption monitoring. Changes in power consumption can indicate a loss of performance due to cavitation. The fifth method of performance monitoring is temperature monitoring. The collapse of cavitation bubbles can generate localized heat. Monitoring temperature changes can be an indicator. The sixth method of performance monitoring is cavitation number calculations. Calculate the cavitation number at different operating conditions and compare it to the critical cavitation number for the device to determine the likelihood of cavitation. Number 5 is other methods. The first is oil analysis. Analyzing the oil for wear debris can sometimes indicate cavitation damage, especially in hydraulic systems. The second is computational fluid dynamics, or CFD, simulation. CFD can model the fluid flow and predict cavitation zones, allowing for proactive design and operational changes. The third is high-speed photography or videography, can be used in laboratory settings to visualize cavitation bubble formation and collapse. The fourth is radiography and ultrasonic testing, or UT. These non-destructive testing methods can identify internal damage caused by cavitation, such as cracks or material thinning, without disassembling the equipment. Number 6 of inspection and monitoring category is choosing the right methods. The selection of appropriate inspection and monitoring methods depends on several factors. The first is type of equipment. Pumps, turbines, valves, propellers, etc., require different approaches. The second is operating conditions, fluid type, pressure, temperature, flow rate, etc. The third is accessibility. How easily can the equipment be accessed for inspection or sensor placement? The fourth is budget, the cost of the inspection equipment and the labor involved. The fifth is desired level of detail. Do you need early warning, or just to assess existing damage? It is often best to combine multiple methods for a comprehensive assessment. For example, combining visual inspection with acoustic monitoring, or performance monitoring with vibration analysis, can provide a more complete picture of cavitation damage. Early detection and preventative measures are crucial to minimizing the impact of cavitation on equipment life and performance. Thank you.